Hello everyone, welcome to this channel. If you're new here, my name is Hasan. Let's begin our 20th part of the video series. In this video, I'll be discussing about the concept of simple microscope and compound microscope. First of all, I'll explain the concept of visual angle because this is one of the most important parameter while understanding the concept of magnification in simple microscope and compound microscope. So first I will explain the concept of alpha and beta, and then we'll use that concept in deriving the formula of magnification in simple microscope and compound microscope. I'll take my time to explain the concept of simple microscope because if you just understand the concept of simple microscope, then compound microscope will be absolutely easy because compound microscope is just the extension of simple microscope. And finally, after deriving the formula for magnification in compound microscope, I'll give you a formula that will help you to understand the relationship between focal length and magnification. Now in compound microscope we use two lenses, like two convex lens. One is known as the eyepiece lens, another is known as the objective lens. Now how are the focal length of eyepiece and the focal length of the objective lens responsible for magnification? We'll be looking into that because in one of the year in NEET, question was asked based on that concept. If you just understand the basic concept of simple microscope and compound microscope, questions that are asked in NEET from this part is very easy because most of the time questions are formula based, and if you just know the formula you can solve those questions. And sometimes objective questions, that is conceptual questions that are objective in nature, are asked in NEET. So if you just follow this lecture, everything will be super simple. So without any further delay, let's jump into our concept building process and let's roll the intro. Okay, now let's start our study on the concept of microscope. It's an easy topic. If you have understood the concept that I've talked about in my earlier videos, then this is just the simplest topic of all because you have all the concepts that is required to understand this topic. So this is very simple if you have the basic concepts correct. Okay, I'm assuming that you have gone through my previous lecture videos. Then only this thing will be absolutely easy for you. Okay, so let's understand what is microscope. What is the definition of microscope? As you can see, it's written that it's an optical instrument which magnifies a small object. So basically it's an instrument which makes a smaller object looks bigger. Okay, so this is a very useful instrument. In order to understand the physics of microscope, the first term that you need to understand is the distance of distinct vision. So this is the term that you need to understand first. So what is distance of distinct vision? As you can see, it's written on the screen that the minimum distance up to which the object can be viewed distinctly. Okay, this is known as distance of distinct vision. But what does it actually means? Let me make this thing very clear by drawing the diagram. So let's see. Suppose this is our eye. Okay, I know it's not pretty, but it will do the job. This is our eye and we have kept a small object somewhat here. Okay, this is our object O. Now, if we bring this object closer and closer to the eye, what will happen? This object will start to seem bigger and bigger, isn't it? We know that whenever we bring things closer to the eye, the object starts to become bigger. So similar is the case here. As we are bringing the object, we will start to see that same object bigger and bigger, and we can see the object more clearly. Okay, this is a small object. I hope this much is clear. Now let's understand. Now as we are bringing this object closer and closer, there is a point at which the object seems to be the biggest, okay, as well as the clearest. This is very important. This is very important. The object not only seems to be biggest but also the most clearest of all. Okay, now if we start to move this object more closer to the eye, what happens? The object will start to become more bigger, but one thing will happen. The object will no longer be clearest. It will start to become hazy. Okay, it's very easy. You can take a small object and bring it very closer to the eye. You will see that object becoming bigger, but if it is very close to the eye, then you'll see that object as a hazy object. So this point, okay, this is the point where we are seeing the object the biggest and the clearest. So we term this point as capital D, and we say that this minimum distance from the eye is actually known as distance of distinct vision. I hope this much is clear. It is denoted by capital D, and we have seen that D for normal human being is 25 centimeter. Now the value of D varies according to age, like a person with old age will have different value of D, but for normal human being the value of D is always 25 centimeter, near about 25 centimeter. So this is the concept of distance of distinct vision. Okay, if you have understood the concept of distance of distinct vision, then the concept of magnification for microscope will be absolutely easy. I hope it is clear. Now let's move on to our next concept, that is visual angle. Now let's look into the concept of visual angle. Now why visual angle is important? We know, what does microscope do? Microscope actually magnify object. Okay, we know the formula for magnification is height of image divided by height of object, and this concept has been explained in my earlier video, isn't it? But here we won't be using height of image or height of object to find magnification in microscope. Rather, in microscope we will be mainly using the concept of a visual angle. So I've written it down for you that in microscope we don't deal with object height or image height. We mainly use the concept of visual angle. So this is the thing that we need to understand here. Visual angle, as you can see, that it is the angle found by the object at our eye. Now this thing will be clear if you look into this diagram. So this one is our object. Okay, so this will produce some angle in our eye. As you can see, this is the ray and this is another ray. If two rays go and hit this eye, then we'll see this angle. This angle is actually the angle subtended in our eye, isn't it? Now, if you look next, the height of the object is directly proportional to visual angle. Now for magnification, we need height of image and height of object. But here we are using visual angle. So since we are using visual angle, there has to have some kind of relationship between visual angle and height of image and object. If you look here, then I've written it down for you that there is a relationship between height of object and visual angle. And you can see that height of object is directly proportional to visual angle. In order to understand this, let's see if this is the height of the object and theta is the angle produced in the eye, okay, or the visual angle is theta for this object. Okay, now if I take another color and if I make this object bigger, then you'll see the angle subtended at our eye will be bigger, isn't it? So bigger the object, bigger is the visual angle. As you can see, I've written it down for you that height of the object, that is, greater the height of the object, greater will be the visual angle. Smaller the height of the object, smaller will be the visual angle. So there is a relationship of height with visual angle. So you can replace this formula that is represented in terms of height in terms of visual angle. So we'll be using that in microscope. So let's look into that and see how we are applying that. Now magnification, we know, let me write it down for you, that magnification is height of image divided by height of object. This is the basic concept, and we have seen that the height of the object is related to visual angle, isn't it? So we can say that this height of the angle is directly proportional to the visual angle found by the image, and height of the object is directly proportional to the visual angle found by the object kept at D. I will explain that, so don't worry. First of all, understand this part. Height of the image is directly proportional to the visual angle found by the final image. This visual angle that is found by the final image is given by or written by beta, okay, and the visual angle found by the object kept at D is written as alpha, okay. Therefore now we can replace this formula of magnification hi by ho as m is equal to beta by alpha, as I've written it down here, isn't it? I hope this is clear. Now let's understand the last part of this equation, that is visual angle formed by object kept at D. Why we are using this, that is visual angle found by object? We should have taken the object at any distance. Why specifically at capital D? This is the most important thing that you need to understand. Now we know that what is D? D is actually distance of distinct vision. Now distance of distinct vision is the minimum distance of the object from the eye, where if we keep the object, then we see the object the biggest as well as the clearest, okay. So if this is our eye, okay, and this is the object and this distance is capital D, then at this position we'll be looking into this object the biggest and clearest. I hope this is clear. Now after which if we move this object closer to the eye, then the object will become bigger than this, but it will be hazy. So our eye can only make things bigger up to this level, that is up to capital D. After which if we want to make the object bigger than that, then we need to use the optical instrument known as microscope. Therefore our ability of the eye without microscope where we can see the object, the clearest and the biggest is at. Therefore, we'll be keeping the object at that position so that we get the biggest object and the clearest object, and then we will magnify that object. Okay, I hope now the concept is clear. Therefore, we are keeping the object at D and then magnifying it. As a result of which, we use the visual angle that is formed when the object is kept at capital D, and we got the formula to be m is equal to beta by alpha. I hope this is clear. Okay, so now let's jump into our next concept, that is the concept of simple microscope. Now, once you've understood the concept of visual angle and the concept of distance of distinct vision, the concept of simple microscope will be absolutely easy. Now, what is simple microscope? It is basically a convex lens where the object is kept between focus and optical center. We have learned all these things as just a kind of revision. We know that for a convex lens, when we keep the object between focus and optical center, then the image that is formed is actually virtual in nature and it is magnified. So we'll be using that property of convex lens. Okay, so let's see. If you look into this diagram, we'll see that if this is the focus and this is the optical center and the object is kept in between focus and the optical center, then we require two rays for formation of image. This thing you already know. This is the first one and this is the second one. The first ray is parallel to principal axis. After refraction, it will pass through focus, okay, or you can say F2, primary focus, and the second ray will go through the optical center and it will go undeviated. Now these two rays are diverging rays, they will never meet, and if we extend these two rays backward, then we'll see that it will meet at a point, and the point of intersection is actually virtual in nature. Therefore, the object form is virtual and it is magnified, as you can see it here. So this is how the image is formed in simple microscope. So it's very easy. We can simply say simple microscope is a convex lens where the object is kept between focus and optical center. Okay, and we'll get a magnified image. And the nature of the image that is formed is virtual in nature. Now let's understand, in order to find magnification, we require two things. We know that magnification is beta by alpha. So we need to understand the beta and the alpha part here in this scenario. So let's understand the first parameter, that is beta. Okay, now beta is the visual angle subtended by the image, that is by the final image at our eye. Now this is our final image, as you can see. Okay, now it is producing angle beta at our eye. Okay, so this is the angle beta. Now if you look into this figure, we will see that tan beta is height by base. Okay, but there is another formula. If you look carefully, then you will see that tan beta is also this height, that is HO divided by this. We'll get the same answer. But since this distance is unknown to us, the image distance, but we know that the object is kept at U, we know this distance, we also know the height of the object used. Therefore, instead of using this and this for tan beta, we will be using this height and this base. I hope this is clear. So we can say that tan beta is equal to HO by U. Okay, I hope this is clear. So we got tan beta is HO by U, where HO is the object height and U is the distance of the object from the lens. Simple as that. Now since beta is very small, we can use tan beta is equal to beta. This thing I have already explained in my earlier videos. So tan beta can be written as beta since beta is very small. Why beta is very small? Because the object that we are using to inspect, we know that the object is very small. If the object is big, then there is no use of magnifying it. Since the object is very small, the angle subtended by that object will be very small. Therefore, you can say that tan beta is equal to beta. Therefore, beta we got is equal to H naught by U from this diagram. Okay. Now, since we have understood what is beta, now let's analyze the concept of alpha. Alpha is the angle or the visual angle subtended by the object when it is kept at D. We have looked into this earlier. Okay, the two important things that you need to understand in order to understand alpha is that alpha has nothing to do with microscope. Okay, the angle that is produced by the object at our eyes, that angle is alpha when we are not placing any kind of microscope in between it. It is the direct angle produced by the object at our eye without the use of any kind of microscope. I hope this is clear. Therefore, I've written it down here that it is the angle subtended by the object in the absence of microscope when the object is kept at D. So basically we can say that alpha is most of the time constant for a particular object. Why I'm saying that? Because we know that, let's analyze this diagram and things will be clear. Suppose this is our object HO having height HO and is kept at a distance d, and we know that d is constant. Okay, d is equal to 25 centimeter, which is constant. Therefore, tan alpha can be written as perpendicular by base. Here the perpendicular is HO, and this HO is constant for different object. Okay, once we know the value of HO, then that value remains same for that object, and the base is d, which is again constant, which is 25 centimeter. Therefore, we can say that alpha is basically constant, okay, for a particular object. And since we know the object that we are using is very small, therefore the alpha will be very small. That is, the angle subtended by that very small object will also be very small. Therefore, we can say that tan alpha can be written as alpha is equal to h naught by d, since alpha is very small. I hope the concept is clear. Now we will apply the value that we received for beta and alpha in the formula of magnification. We know that magnification is beta by alpha, that is the angle subtended by the final image at our eye when microscope is used, and alpha is the angle subtended by the object at our eye when the object is kept at distance of distinct vision when no microscope is used. I hope this is clear. Now just put the value of beta and alpha. We have got beta as h naught by u and alpha as h naught by d. Just h naught will get cancelled out, and we got magnification of simple microscope as d by u, where u is the object distance. Simple as that. Now this is the basic formula for magnification for simple microscope. Now we'll be looking into two different cases of magnification in simple microscope. So first case is maximum magnification. So let's dive into that. So in microscope, when can we get the maximum magnification? Let's look into that. Now, in order to understand that, let's start with a question. The question is, where can you see the object distinctly and also the biggest? Okay, this thing I have explained. There's a distance in front of the lens where we can see the object distinctly and also the biggest. Okay, and that distance is known as distance of distinct vision, and normally the distance is 25 centimeter. Now, if this is our eye, and this is the distance of distinct vision, then if we bring the object closer to the eye, then what will happen? The object will become bigger than that, but it will be hazy. That is, the clarity will decrease. The clarity and the size is maximum at this point. Okay, this is distance of distinct vision. So now let's understand, when we keep the object at d, then we are getting the best and the biggest image. Now my question is, look into this diagram. This is our image, okay, hi. Now if this image is formed at d, suppose this is our point of d, okay, if this image is formed at d here, then we can say that the image that will be produced will have the maximum size and the best clarity. Okay, because as we bring this image closer, we are going to see the image more bigger and bigger. Okay, and when it reaches d, then the image will be the biggest and it will also be having the highest clarity. Okay, now if the image crosses d, then what will happen? The image will become bigger, but the clarity of the image will be lost. That is, the image will become hazy. Okay, so the concept that you need to understand here is that the object will be having maximum magnification when the image is formed at d. Okay, so this is the concept I need to make you understand. Now once this is clear, then the derivation of the formula is very easy. Now let's look into this figure and let's see. We know magnification formula is d by u, isn't it? This is the thing we have already derived in our earlier case. Now my question is that you know that for magnification the image should be formed at capital D and the focal length of the convex lens is always mentioned. Okay, then how to find where should be the object kept, that is this object, in order to get the image at D? This is the thing. So what should be the formula that we need to use? We know f, we know the image distance, we just need to find out this u. How to find out? The only formula that will help us to achieve this is Lenz's formula, and we know the Lenz's formula is given by 1 by f is equal to 1 by v minus 1 by u. For convex lens, focal length is always positive. Okay, so f is positive, is equal to, now v is at d, okay? And from the sign convention, we can say that it will be minus d because the direction of incident ray is in this direction. So this should be taken as positive, and our calculation for d, or the image distance, is in this direction from the pole. So it will be negative. And we need to find out u, and we know the direction of u will be in this direction. Okay, so it will be minus u. I hope the sign convention is clear. Now if we solve 1 by u, then from here we can say that 1 by u is equal to 1 by f plus 1 by d. Now once this is clear, then we got our answer, that is magnification is d by u, isn't it? This is the formula we know. Now if you just put the value of 1 by u that we have got here, then what we will get is d, and 1 by u, this 1 by u can be replaced by this formula, that is 1 by f plus 1 by d. And if you just take the d inside the bracket, then we will get 1 plus d by f. So this is our maximum magnification when the image is produced at distance of distinct vision. Okay, so this is the thing you need to understand. If the question is asked what will be the maximum magnification for a simple microscope, then you need to use this formula, that m is equal to 1 plus d by f, where f is the focal length of the convex lens and d is the distance of distinct vision. If it is not mentioned, then you have to use 25 centimeter. Okay, so this is case number 1. Now let's dive into case number 2. Now let's look into the second case, that is magnification for relaxed eye. Now I'll explain what is magnification for relaxed eye, so don't worry. First of all, understand that this scenario will not produce maximum magnification. In order to produce maximum magnification, we need to use the earlier case, that is, we need to put the image at a distance of distinct vision, and we got the magnification m to be 1 plus d by f. That will produce maximum magnification. Now what is magnification for relaxed eye? Now if you look here, the earlier case that we have seen magnification, that magnification is for strained eye. Now what do I mean by strained eye? Let's understand. Suppose you're given to carry 2 kg of load in your hand. Okay, in the initial stage, you won't find any kind of problem. You'll be easily carrying those 2 kg of weight. But if you keep those weight in your hand for a long time, for example maybe for 20-30 minutes, then what will happen? Your hand will start to get fatigued and you'll feel the pain. Okay, so when our muscle are working for a long period of time, then what happen? Our muscle get fatigued and we feel the pain. That is known as strained. Strained means feeling pain. So I'll write it down for you. It's basically pain. Now let's understand. When we use this scenario, our eyes will start to pain. Now why is this case? For example, let's understand this. Suppose this is the lens, okay, and we have kept the object here. Now parallel rays will come, and what will happen? It will converge to this point in order to see that object, isn't it? Now as I'm bringing the object closer to the lens, then what will happen? I need to converge those rays more sharply, isn't it? I need to converge those rays more sharply in order to focus onto that object. Now let's understand. Let's draw again. Now the rays are parallel, so if the object is now in this position, earlier it was here. Okay, now the rays should converge more. And in order to converge more, earlier case the focal length was this, in this case the focal length is this, isn't it? So the focal length has to decrease. Now in order to decrease the focal length, what we need to do is we need to increase this curvature. We need to increase this curvature. Greater the curvature, we know, smaller is the focal length. Simple as that. Okay, how I am getting this? See, if the circle is bigger, we can say the curvature is small, isn't it? So our center is this. We know focal length will be half of center of curvature, somewhat here. But if our circle is small, what will happen? We say that the curvature is high, isn't it? If the curvature is high, then the focal length will be small, because if this is center of curvature, focal length will be small. So greater the curvature, curvature means the roundness. Greater the roundness, smaller will be the focal length. Okay, now let's understand. If this is our eye, okay, and the object is placed here. Now once we are bringing the object closer to the eye, what happens? Our eye has muscles around it. Okay, so these are the muscles, and these muscles are known as ciliary muscle. Ciliary muscles. These ciliary muscles, in order to focus the closer object, what it will do? It will push the lens in this direction, as a result of which this lens will become like this. That is, the lens will converge, okay, become more round, as a result of which now the rays will bend or converge in a much sharper way in order to focus the object. Now let's understand. If this muscle keep on working for a long period of time, then what will happen? The muscle will get fatigued and you'll feel the pain. Therefore, you have seen that when we read or study books very close to the eye for a long period of time, then what happens? We get headache and our eye feel that pain. Why is that? It is because auxiliary muscles are constantly working to focus the text in the book. Okay, so this working of muscles and the pain that is causing due to the working of these muscles is known as actually straining. I hope this is clear. So basically the pain that we go through is actually known as strain. So in the earlier scenario, if we look through the microscope for a long period of time, in those scenarios, our eyes will feel pain after looking through the object for a long period of time. Okay, but when we look into this second scenario, we'll get magnification in such a way that our eyes will not feel the pain even if we look into that image for a longer period of time. That's why this case is important. Okay, so this case is known as relaxed eye scenario. Okay, so let's see. We know our eyes won't feel pain when the rays coming to our eyes are parallel. That is when the object is far away. Okay, so this is the concept that you need to remember. For relaxed eye, rays should come to our eyes parallelly. Okay, now one concept I have already talked about. When does rays comes parallelly to our eyes? What is the answer? Rays will be parallel when object is far away, or we can say when the object is at infinity. Okay, simple as that. Now we want to look into the image that is formed due to the microscope. We want to look into that image in such a way that our eyes do not get fatigued or our eyes doesn't get strained. Therefore, the image that should be formed should be at infinity. Then if we look into that image, our eyes will not get fatigued, isn't it? Therefore, we know the focal length of the convex lens that we are using. We know the image distance should be at infinity. So where should we keep the object? So we can find out object distance. Where should we keep it? So we know two of these things easily. We need to find this and our things will be very easy because we know magnification is d by u. So we need to find out u, that is object distance, in order to set up this scenario. Okay, so let's see, it's easy. We'll be using Lenz's formula. So Lenz's formula says that 1 by f is equal to 1 by v minus 1 by u. Now we know that focal length is positive for convex lens. Therefore, we can say that 1 by plus f is equal to 1 by v. Now the image that is formed should be at infinity. Okay, therefore we will write this as infinity. Doesn't matter. I know it will be negative because the image formed should be virtual. Okay, on the same side of the lens. Therefore, it will be virtual and the diagram has been done in the earlier case. Okay, so it's easy. Doesn't matter whether minus or plus, 1 by infinity will always be 0. Minus 1 by u. Therefore, if we just find out what is 1 by u. Now, I have missed out that u should be negative according to sign convention. Therefore, we can say that 1 by u is equal to 1 by f. Now, if we put the value of 1 by u in this equation, then we will get, let me pick another color, we will get m is equal to d and 1 by u is 1 by f. Okay, so we can say f. So magnification will be d by f for relaxed eye scenario. But this is not the maximum magnification. You need to remember this. For maximum magnification, m should be, m is equal to 1 plus d by f. Okay, so this will create strained eyes if you look into the image for a longer period of time, and this is for relaxed eyes. I hope now this is clear. This is very simple. You just need to understand the concept. Okay, you don't need to memorize everything blindly. It's impossible to remember after going through all these numerous number of chapters. Okay, so you need to understand the concept. So this is how you need to remember. Okay, so once we've established this, a little bit is just left, that is range of magnification. Range of magnification in simple microscope. What is the range? The range is d by f and 1 plus d by f. Okay, so this is the range. Magnification is from d by f to 1 plus d by f, where 1 plus d by f is the maximum. So this is the range of magnification for simple microscope. Now let's move on to our next concept. Before jumping into our new concept, we'll just look into this bird's eye view of the concept that we have learned recently, so that these cases that we have learned is case 1 and case 2, that is for maximum magnification, normal magnification, this becomes absolutely clear because we'll be using these case 1 and case 2 while studying compound microscope. So these things need to be absolutely clear in order to make the next concept very easy. Okay, so now let's look into case 1 and case 2 in the form of comparison. So let's see. In case 1, we see that maximum magnification occurs and the value is m is equal to 1 plus d by f. Okay, so this is the case for maximum magnification. The second case was for normal magnification, where magnification was given by d by f. Okay, this is not maximum magnification, whereas case 1 gave maximum magnification. Okay, if you look into point number 2, then we see that when we got maximum magnification, the image formed was at distance of distinct vision. When the image is formed at distance of distinct vision, then only we get the maximum magnification. Okay, and we know the distance of distinct vision is a closer distance, that is 25 centimeter. Therefore, since we are focusing things that are closer to our eyes over a long period of time, we get pain in our eyes, and as a result of which we say that we are having strained eyes. Okay, as I've written it down here, that the image formed at D that is closer, therefore strained eyes over long observation. If you keep on looking into that image for a longer period of time, you will have strained eyes or you'll have pain in your eyes. Okay, for second case, we can see that the image formed is at far away distance, or in mathematical terms we can say that is the image is formed at infinity. Therefore, we won't have any kind of pain in our eye when we look into that image that is formed over a long period of time. Therefore, I've written it down, that is therefore relaxed eyes over long observation. I hope this is clear. So whenever the image is formed at a closer distance, we need to focus and our muscles need to work, that is ciliary muscles. Now since that muscle is working continuously over a long period of time, the muscle will get fatigued, simple as that. And here our muscle is not actually working, okay, it is relaxed, therefore we will not have any kind of pain. And we have seen that magnification in microscope is given by d by u. This is the base formula. Now if you look into case number 2 for relaxed eye, I said that the image should be formed at a longer distance, or you can say that it is formed at infinity. We know that when is image formed at infinity? When the object is kept at focus. So we can say that u will actually get replaced by f, that is the object should be kept at focus in order to get the image at infinity. Therefore, in this case, we got m is equal to d by f. Just replace u by f. We have used the lens maker's formula, that is 1 by f is equal to 1 by v minus 1 by u. Now put v is equal to infinity and you will get that 1 by f is equal to 1 by u, because u will be taken as negative according to sign convention. We have learned this. So it's very easy. You don't need to remember this formula. This is very easy. You just need to remember the base formula and just derive it within 5 seconds. Okay, now how to derive this? If you just remember this formula, then remembering this formula, that is maximum magnification, is very easy, because see, this magnification should be greater than this, isn't it? Because this magnification is actually maximum magnification. What you need to do is just add 1 to make it bigger than this, isn't it? So make it d by f. So this is the easiest way of remembering things. Otherwise, what you can do is 1 by f is equal to 1 by v minus 1 by u. Okay, we know the image should be formed at distance of distinct vision, so this will be replaced by minus d, and this u will be replaced by minus u according to sign convention, and then find the value of 1 by u and just replace it here and you will get this value. Simple as that. So this is the synopsis you need to understand. Okay, if you understood this concept, then the concept of compound microscope will be absolutely easy. So let's now jump into compound microscope. Okay, now let's look into the concept of compound microscope. If you have understood the concept of simple microscope, then this part is absolutely easy. If you look into this diagram carefully, you'll see that in compound microscope, we use two convex lenses. Okay, in the earlier case, we have used a single convex lens where the object was placed between focus and the optical center. Okay, here we have used two lenses. One of the lens is known as objective lens and another lens is known as eyepiece. Now, why this lens is known as eyepiece? Because this lens is closer to the eye. We look through this lens, therefore this lens is known as eyepiece. Whereas this lens is known as objective lens because this lens is kept closer to the object that we are observing. Okay, I hope this is clear. Now, objective lens is small, therefore it will have a smaller focal length, whereas eyepiece is actually big and bigger than the objective lens, therefore it will have a bigger focal length. Okay, Now let's understand the diagram. Here, what we are doing here in this concept is that we will magnify the object twice, once by the objective lens and then by our eyepiece lens. Let's understand now that AB is our object. Okay, this is the object that we need to magnify. Now we know from the concept of convex lens, that is the image formation by convex lens, that whenever the object is placed between f and 2f, then what happens? The image that is produced by the convex lens is real, inverted and magnified. Okay, this thing we have learned. So we can see that we got the image A dash B dash, which is real, inverted and magnified. Once we have got this image, then what happened is that this image A dash B dash acts as a virtual object for the eyepiece. Okay, this thing we have learned earlier in my earlier video, that whenever combination comes into play, then the result of the first combination actually acts as a virtual object for the second combination. I hope this is clear. So now A dash B dash will act as a virtual object for the eyepiece. Now, if you look carefully, I said that the eyepiece has a bigger focal length, isn't it? So that the image that is produced, that is A dash B dash that is produced, will fall between focus and the optical center for the eyepiece. Now you know the drill. Okay, we have explained this in Simple Microscope, that whenever an object is kept between focus and optical center, then what happens? The image that is produced is virtual, erect and magnified. Therefore, if you look into this diagram, you'll see that A dash B dash is producing an image that is A double dash B double dash, and it is virtual and magnified. Now, why it is known as virtual? As you can see that this is the ray, suppose this is one ray and this is our second ray, and both the rays after refraction diverge away. Therefore, they will never meet. Now, if you extend both the rays backward, we can see that they coincide here. Therefore, we got an image due to false intersection, not real intersection. Therefore, this image is virtual. This thing I have already explained. So once you have understood that this is the process by which the image is formed, that is, first of all, this object is magnified by objective lens and we got the image here, and again this image is magnified by the eyepiece and we got the final image to be this one. I hope this is clear. Now let's look into the concept of magnification. Now we know that magnification in microscope is given by beta by alpha, where beta is the visual angle formed by the final image at our eye. Simple. And alpha is the visual angle formed by the object kept at D, where D is the distance of distinct vision, 25 centimeter, at our eye in the absence of microscope. This is very important. I've taken my time to explain this concept. Okay, so once this is clear that magnification is beta by alpha, now let's move on and see our diagram whether we can recognize which one will be beta. Now if you look carefully into the diagram, then you'll see that this is A dash B dash, or the final image. Therefore, we need the angle subtended by this final image in our eye. So if you look carefully, then this angle is the angle subtended in our eye. Therefore, we'll say that this is beta, isn't it? Now, if this is beta, we know we need to find beta by using the concept of tan beta. Okay, now tan beta can be written as beta because the object is very small. A dash B dash will be very small because we are magnifying a small object. Therefore, A dash B dash has to be small. If A dash B dash is small, then beta will be small, and therefore you can write that tan beta is equal to beta, according to mathematics, is equal to A dash B dash divided by UE. Now we know that tan theta is equal to perpendicular by base. The perpendicular here is A dash B dash. If you look carefully here in this diagram, then this is our perpendicular. Let me pick another color, and this is our base. Okay, if you look carefully, then we can see that A dash B dash is actually the virtual object for the eyepiece. Therefore, you can say that A dash B dash, since it is the object for the eyepiece, therefore this distance can be termed as object distance for eyepiece. So that will act as a base. Therefore, A dash B dash is the perpendicular and UE is the base. Now what we need to do in order to find the formula for beta, we'll replace A dash B dash in terms of U, V and H. Okay, because those are the most important parameters. Now in order to replace this value of A dash B dash in terms of U, V and H, what we will do, we'll look into the first combination, that is the objective lens. Now magnification in objective lens, we know that in lenses, magnification is given by height of image by height of object, isn't it? Now if you look carefully into the diagram, let's go back. The height of the image by height of the object. Now height of the image is A dash B dash for objective, and AB is the height of the object, isn't it? So A dash B dash by AB, isn't it? So we got, as you can see, A dash B dash by AB. Now I have used negative sign for A dash B dash because A dash B dash is basically inverted, and we know from the sign convention that inverted height is taken as negative. Okay, so this is clear. We have another formula for magnification, that magnification is given by V by U, that is image distance by object distance in lengths. Okay, now if we go back to our figure again, we will see that this is our VO, that is image distance, and this is our object distance in terms of objective lengths. If you look carefully the sign convention, then V will be positive and U will be negative. Why? Because our direction of incidence is this side, this will be taken as positive, and our calculation should be starting from the pole. Therefore, if we move in this direction, we can calculate U, therefore U will be negative, and if we move in this direction, we will calculate V, so V will be positive. I hope this is clear. So let's put the value here, and we got V by U as V naught by minus U naught. Simple as that. Now if we combine equation 1 and equation 2, then we can say that minus V naught by U naught is equal to minus A dash B dash by AB. Simple. Now this negative will get cancelled. Now you can find the value of A dash B dash, which is actually our required target. So we got A dash B dash in terms of H naught, V naught and U naught. Once we get the value of A dash B dash, now we will put the value of A dash B dash here directly. Okay, and we can find the value of beta in terms of H, V and U. So what we have done is we have put the value of A dash B dash here, and we got beta is equal to H naught V naught divided by U naught by UE. I hope this much is clear. So the concept of beta is done. Now we need to find out alpha, and alpha is very easy. It's basically constant. We know that alpha is the angle subtended by the object when it is kept at D. So suppose this is our object, okay, having height H naught, and it is kept at a distance D, and this is our I, okay. Then the angle subtended at our I will be alpha. Therefore, you can see from the figure that alpha is perpendicular is H naught and base is D. Okay, so we got the value of alpha also. Now we got alpha, we got beta. Now it's simple, just put the value and you'll get the formula for magnification of compound microscope. Therefore, you can see we have put the value here, beta by alpha. And finally, we got magnification to be this H naught, and H naught will get cancelled out, and we got M is equal to V naught by U naught multiplied by D by UE. This is the base formula for compound microscope. What was the base formula for simple microscope? The base formula for simple microscope was D by U, isn't it? Now this is the base formula for compound microscope. Now if you look carefully, you'll see that this is M is equal to V naught by U naught. What is V by U? V by U is basically magnification for lengths. If you look carefully, then V naught is image distance for objective, U naught is object distance for objective. Therefore, we can say that V naught by U naught is actually magnification of the objective lens. Therefore, we can write down V naught by U naught as MO, that is magnification of the objective lens. And if you look carefully, then D by UE. What is D by U? It is magnification of the simple microscope, that is basically a convex lens when the object is kept between focus and optical center, isn't it? So we can say that basically this is magnification of the eyepiece, because here if you look into the diagram, let's go back, you'll see that this figure here, this part is basically acting as a simple microscope. Okay, I hope this is clear. Now let's move back. Okay, therefore we got magnification is equal to MO multiplied by ME, where MO is magnification of the objective lens, ME is magnification of the eyepiece. You need to remember this formula also. Simple as that. Okay, once this much is clear, my job is done. Now since you have understood that this is basically acting as a simple microscope, so we can say that the eyepiece is acting as simple microscope Therefore, it will show all the properties that a simple microscope show. We have already studied simple microscope and we know that there are two cases for simple microscope for magnification. One is maximum magnification, case 1, and case 2 was normal magnification. So let's build that. So case 1, and here we can say that this will be case 2. Now case 1 is maximum magnification. So we can write it down here, maximum magnification, and here case 2 is normal magnification. Okay, now maximum magnification and normal magnification. In normal magnification, our eyes were relaxed. That is, the image found was at infinity. That is, the final image was at infinity. Okay, and we got that for simple microscope, for normal magnification, the formula is m is equal to d by f, isn't it? Therefore, we can just use this formula and write it down as, for compound microscope, for normal magnification, it will be V0 by U0. We won't touch the magnification of the objective, but since our eyepiece is acting as a simple microscope, we'll be using the formula for normal magnification in microscope here. Okay, so it will turn into D by FE. Okay, instead of UE, we'll be using FE for normal magnification. Whereas for maximum magnification, we know that m will be V0 by U0. This is the magnification of the objective. We won't touch into this, multiplied by, see, this eyepiece is acting as a simple microscope, and we know that for simple microscope, maximum magnification occurs when the final image is produced at distance of distinct vision, and we used Lenz's formula and derived it in our earlier case that maximum magnification for simple microscope is 1 plus d by FE. Okay, so everything remains same, just change the magnification of eyepiece accordingly, because the eyepiece is actually acting as a simple microscope. So when maximum magnification is attained, then the eyepiece is actually acting as case 1, and whenever there is normal magnification, then the eyepiece is actually acting as case 2. Okay, I hope this is clear. I won't derive this because I have already derived it in the case of simple microscope. I hope this is clear. So this is all about the concept of compound microscope. This is super simple. You just need to remember that magnification of compound microscope is given by magnification of the objective multiplied by magnification of eyepiece, where magnification of objective, just put the formula of magnification of lens, that is V0 by U0, and magnification of eyepiece, basically eyepiece is acting as a simple microscope, therefore just put the base formula d by UE. Okay, now change this d by UE according to case 1 and case 2. If it is maximum magnification, then use this formula. If it is normal magnification, then use this formula, and it's done. I hope the concept is clear. We are almost done with compound microscope. Only a little bit is left. We'll look into that and we'll wrap up the concept of compound microscope. So let's look into our final concept. If we move down, and this is our compound microscope, the diagram. Okay, this diagram we have seen earlier also, so let's understand this again. Okay, we got magnification is equal to magnification of the objective lens multiplied by magnification of eyepiece. Okay, this was done, and magnification of objective lens is given by V0 by U0 multiplied by magnification of the eyepiece is given by D by UE. Now this can be, again, this magnification has two cases, that is maximum magnification and normal magnification. If I say M maximum, that is maximum magnification, this will turn into V0 U0 multiplied by 1 plus D by FE. Okay, and for normal magnification, if I write it down in this way, then the formula will be V0 U0 multiplied by D by FE. These are the things that we have learned. Now let's understand one thing, that how is the focal length of the objective and the focal length of the eyepiece actually responsible for magnification. Question based on this concept has been asked earlier in NEET. So let's understand this. As you can see from the formula here and here, that focal length of the eyepiece is inversely proportional to magnification. So this is easy. But in the formula, there is no such mention of focal length of the objective lens. So how is the focal length of the objective lens responsible for magnification? Let's look into that. If you look closer into the diagram, this diagram, then you'll see that our object is placed very close to the focus of the objective lens. So this is our focus of the objective lens. Okay, and this is our object. So what we need to do is for compound microscope, in order to get good magnification, we keep this object very close to focus of the objective lens. Therefore, we can say that this UO, that is the object distance from the objective lens, can be almost approximately written as FO. Okay, but we never keep the object on focus. This is very important. But for understanding the concept of how focal length of objective is responsible for magnification, this really helps. What will happen to magnification? So the formula for magnification can be approximately written as, instead of UO, we can write FO. Okay, simple as that. So I have used this sign because we never use this formula for finding magnification. This is just in order to understand the concept of focal length. I hope this is clear. In order to find magnification, we either use this formula, or this formula. Okay, but in order to understand the focal length, we use this formula. Now let's understand. This is d by Fe or 1 plus d by Fe according to the case. So we got that FO is inversely proportional to magnification and Fe is also inversely proportional to magnification. You need to understand this. Another question they can ask you is, if you look closely into the diagram, then you'll see that the image that is formed due to the first objective lens is this one, A dash B dash. Now if you move this object very close to focus, then what will happen? This image will move in this side, and we know that when we keep this object on focus, this image will go to infinity. But we never keep the object on focus, we keep the object very close to focus. Therefore this image will be formed very closer to the eyepiece. I hope this much is clear. If this image is very closer to the eyepiece, we can say that the image distance V0 is almost equal to the length of the compound microscope. So this is actually the length of the compound microscope. Okay, now if the image formed due to the objective lens is very close to the eyepiece, suppose here, okay, suppose it is formed here, then we can say that this V0 is almost equal to the length of the compound microscope. Therefore we can say, instead of V0, we can replace this as L, that is length of the compound microscope. So this is just the approximation formula in order to understand how length of the compound microscope and focal length of the objective and focal length of the eyepiece is responsible for magnification. Now if in the question they give you the length of the compound microscope and no other such data is given, then you need to find magnification using this formula. I hope this is clear. So this is the last bit of thing that you need to understand for compound microscope. If you understood this thing, then you're good to go. So this is all about compound microscope. I hope you've understood all the concept that I have spoken about in this video, and all the concepts are super easy. So if you enjoyed this video, then please give it a thumbs up, and if you haven't subscribed to this channel, then please consider doing so. Till next time, enjoy your studies and build your concept, and I will catch you all in my next video. Bye bye.